for my second talk of this workshop, I'll be telling you about something slightly different than yesterday, and it's a framework called distributed PCP. So if you remember yesterday, I was talking about gap ETH, and for that assumption, you already have a gap. You just want to do reduction that create larger gap, like gap amplification, or preserve the gap. But distributed PCP is one way that you can create new gaps in similar manners as Bing Kai's talk yesterday and also earlier today. And just to be concrete, I'll be using 3 problems as example, but there are more results that you can derive from distributed PCP framework. The first problem I will use as an example is the bichromatic closest pair. So this is a very well-studied problem. You are given 2 sets, A and B, and here I denote them by 2 different colors, red and blue. And you want to find points, 2 points, one in A, one in B, that are as close together as possible. Okay? And this is an extremely well-studied problem. Obviously, you can do it in n squared times d time, where you just enumerate all pairs and compute their distance and pick the minimum. And the question is, of course, whether you can do better. So it turns out that if you assume strong exponential time hypothesis, the SETH, then you can do that much better. Okay, so you cannot solve the problem in n to the 2 minus delta time for any constant delta. And this was known already for d that is log n. And this holds even for 0, 1 vectors. So this follows directly from the orthogonal vector if you are familiar with that. If you are not familiar with that, then it's okay. And there are also lines of work that show that you can do dimensionality reduction on this. So in fact, it's very hard even for much smaller dimension than log n. The current best known result shows that even when dimension is exponential in log star n, then it's still hard. And this is also a nice open problem. As far as I'm aware of, there is no algorithm that works for this problem in dimension that is omega of 1, so non-constant dimension. So it is plausible that you can do dimensionality reduction all the way to almost constant. Okay, but that's an open question. That's kind of orthogonal to today's talk. This is the exact version of the problem. Today's talk will be focused on approximate version of this problem. And just to remind everyone, SETH, I guess we have seen it multiple times, but I'm just flashing it up here. Like, we are assuming that you cannot solve for every epsilon, there is L, sufficiently large L, such that you can solve L set in 2 to the 1 minus epsilon times n time. Okay, now let's go back to the closest pair problem and look at the approximate version of closest pair. Again, everything, the setup is the same, but now you don't have to output the minimal, the optimum. You can output a pair of points that is within 1 plus epsilon factor of the optimum. So in this case, there are a bunch of algorithms that work in this setting. Like, for example, you can use approximate nearest neighbor data structures to solve this kind of problem. In some sense, approximate nearest neighbor is harder because it's an online version of the problem. And indeed, like for this offline version, this batch version, you can do slightly better. And if you want 1 plus epsilon approximation for small epsilon, you can save a little bit in the exponent. Okay, so you can get n squared minus a factor that depends on epsilon. And currently, the state of the art is something like epsilon to the 1/3. So now, given this, the natural question is, okay, this saving is nice, but the saving also decreases with epsilon. Now, would it be possible, like if you can fix some epsilon, let's say 1.01, if you can fix the running time, say n to the 1.99, and get 1 plus little o 1 approximation, right? So is it possible that you don't have to trade off this epsilon and the running time and get the little o 1 approximation? And this is one of the results we'll be talking about. So in 2018, Abboud Rubinstein showed that this is not possible. So for every epsilon, if you want 1 plus epsilon approximation, then for every delta, there exists sufficiently small epsilon such that if you want 1 plus epsilon approximation, the running time you need is at least n to the 2 minus delta. Okay, and as I said earlier, closest pair is an easier problem than approximate nearest neighbor. So you get immediately hardness for hardness result for data structure for approximate nearest neighbor as well. And I just want to mention that there are follow-up works that get more quantitatively tight result than this in terms of the trade-off between epsilon and delta, but we will not go into too much detail on that here. Another interesting thing is that the problems I will be talking about today will be the bichromatic version. You might be wondering what happened to the monochromatic version, where you have just one set and you want 2 points in that same set that are the closest. So that's kind of a challenge that is orthogonal to what we are talking about today, but there are some reductions known from bichromatic to monochromatic version. Although in some setting, like in the approximate setting, there is some loss. For example, the base known hardness currently is still n to the 1.5, not quadratic in the monochromatic setting. So that's an interesting open problem, but orthogonal to the distributed PCP framework that we are talking about today. Okay, so for today, we will just focusing on bichromatic setting, and sometimes I will drop the bichromatic prefix just for brevity here. Another nice and very related problem is the maximum inner product problem. Sometimes it's easier to work with maximum inner product problem, so let's also define that as well. So here, as the name suggests, you have 2 sets again, but instead of wanting a pair that are closest, you want a pair of points whose inner product is the largest possible. Okay, and basically the state of the art are roughly the same as what I said for closest pair. And now for the approximate version of inner product, it is slightly different, right? Closest pair is a minimization problem. The inner product is a maximization problem. So now a C approximation means that you want the inner product to be at least 1 over C times the optimum. And it turns out that you can get an approximation ratio that is roughly D over log N. So approximation ratio of D is kind of easy to get, but you can get an even better, something like D over log N in subquadratic time. So the hardness that was shown in the original paper that proposed the distributed PCP framework, the original paper by Abboud and Williams, they show that basically you cannot beat this by too much. So if your dimension is slightly larger than log N, it's already hard to approximate to any constant factor. So in that paper, there is a more regime of parameter, like very large. They can get very large factor of approximation and trade-off as well, but I will not go into like all the trade-off here. Yeah, and similar to before, there are also follow-up work that gets even tighter trade-off, and there is still a question of bichromatic versus monochromatic, but that will be skipped for the purpose of this talk. Okay, so that's the maximum inner product and closest pair. So these two are still kind of look similar, right? They are fine-grained problem. You can solve it in quadratic time. You want to know whether you can solve it in truly subquadratic time. Now we will go through the last problem, which is very different compared to the previous two, which is the dominating set problem. So you have already seen this multiple times, but the problem is just, given a graph and an integer k, decide whether there is a dominating set of size k in the graph. So this problem is very well studied, of course. It's NP-hard, and you can get a log, just the greedy algorithm give you natural log of n approximation, and it's also known by a classic result that is NP-hard to approximate beyond this factor, okay? So that's the NP setting, the non-parameterized setting. Now you can ask the parameterized setting, where you parameterize by the optimum, the k. And again, this just means that instead of looking for polynomial time algorithm, you want FPT algorithms which run in some tk times poly of n time for some function t. And this was already mentioned yesterday as well, that this problem is complete for the class W2. And of course, there is a trivial algorithm for this problem, which is just to enumerate all possible k size subset and then check whether it's a dominating set. Okay, so you have to enumerate n to the k possibility, and the checking takes another n time, so that's why it's n to the k plus 1. And it turns out that you can shave off this plus 1, and you can get n to the k plus little o 1 running time too. And on the lower bound side, if you assume ETH, then you can show that you cannot get n to the little o of k time. And I think at this point, everyone already know ETH, but I'm just flashing it up here. Finally, if you assume SETH, you can get very tight running time. You get that n to the k minus epsilon time. Exact algorithm for this problem is not possible. Okay, so almost matching the state of the art n to the k plus little o 1. Okay, so this is the states of the exact version of this problem. As you can see, it's fairly well understood. Like everything is pretty tight here. But then you can ask, okay, what happens if you combine the parameterized complexity with approximation algorithm? And here we are looking for an approximation algorithm whose approximation ratio is tk, where t is some function of k. Okay. So just to be clear, this means that if there is a dominating set of size k, you should output a dominating set of size at most k times tk. And yeah, it has been asked since the very early day of parameterized complexity whether this is possible. And there was quite a lot of work even before the distributed PCP. So one of the early success come from Shen and Lin, who show that it's W1 hard to approximate to any constant factor. And if you assume ETH, then they can get a better approximation ratio up to roughly log k to the 1/4. And later on, assuming gap ETH, we show that actually you cannot get any tk approximation in FPD time for any function t. So it's totally inapproximable. And this is the line of work that was related to what I talked about yesterday. But as I said earlier, this is kind of easy because you already have a gap. You just have to make the gap larger. Just have to amplify the gap somehow. But what the distributed PCP framework comes in is when you start from assumptions that you don't have any gap. Okay, and what we can show under this framework is first is W1 hard to approximate to any tk factor. So total inapproximability under W1 hardness. Under ETH, we get the same hardness against, but we get a better running time lower bound of n to the little o of k. Okay. Now, if you further assume SETH, we also get a better running time lower bound of n to the k minus epsilon against any tk approximation algorithm. Okay, and note here that under ETH and SETH, the running time lower bound is the same as the exact version, but now it holds even against approximation algorithm for any tk approximation factor. Okay, and finally, this might be a little bit strange, but we will also show a lower bound under the k-sum hypothesis as well. It's kind of nice to demonstrate it as part of an example of this framework. And Amir already mentioned the k-sum hypothesis, but let me state it again because we will use it. So in k-sum hypothesis, you have k sets A1 to AK, or each set consists of a bunch of at most n numbers. We can assume without loss of generality that these numbers are integer between minus n to the order of k. Here I write n to the 2k to n to the 2k. And the problem here is you want to determine whether you can select one number from each set such that the sum is 0. Okay? And under the k-sum hypothesis, we also prove the hardness, the total inapproximability with running time lower bound n to the k over 2, ceiling of k over 2. And, oh, sorry, that's the K-sum problem. The K-sum hypothesis say that this problem cannot be solved in time better than n to the ceiling of K over 2. And this is the running time you can get if you do a meet in the middle kind of algorithm. Okay. Okay, so just to wrap this up for dominating set, there are indeed subsequent paper. Bing Kai described already the threshold graph framework yesterday. So that is one one other possible construction to prove hardness approximation for set cover. And in fact, it gives a slightly better approximation ratio if you measure it in terms of n. And finally, there is also a newer paper by Bing Kai and others that show that any constant factor approximation is W2 hard. Okay, and note here that before this, it was not known whether it was W2 hard to approximate to even any constant factor. Okay, so just to quickly take a step back, I told you about 3 problems, right? Maximum inner product, closest pair, and dominating set, and there are a bunch of hardness results that we will show today. And perhaps the interesting thing here is that all these results will be shown using the same framework. Okay, so as you will see in a moment, everything is like almost the same. And this is the framework that is sometimes called distributed PCP. So let me describe the framework, at least the way I view it quickly. So you start from the assumption, the hardness assumption that you like. It could be SETH, ETH, K-sum hypothesis, or W1 hardness. Okay, and in the first step, we will rewrite it in terms of what we call a product space problem. I'll tell you in a little bit what this means. It's just some pre-processing so that the assumption is kind of nicer to work with. And now this second step is the interesting step. So this second step is the step that creates the gap. Okay, and this second step is perhaps the most important step in this distributed PCP. And what we will do is we will, by giving some communication protocol, we will take the communication protocol that has good enough efficiency and turn this into a reduction from this PSP problem to max cover in a way that this max cover will have a gap. Okay, and recall again, we start from problem with no gap, but we end up with hardness of max cover with some gap. And max cover, I will also tell you in a moment what it is. It's just one of the variants of label cover. In fact, Bing Kai also talked about it yesterday. And the last step is, of course, to reduce the label cover problem to the target problems that you want to prove the hardness for. Okay, and this is perhaps the most standard of the bunch. Okay, so that's the framework. Okay, so now let's try to go through it step by step. As you can see here, the problem that is at the heart of this framework is this label cover variance, which we call max cover. So let's quickly go over it so that we know the definition and we can go from there. Okay, so what is a max cover? So a max cover instance is consists of first a bipartite graph. And for each left and right hand side, the nodes are partitioned into what we call supernodes. Okay, now there will be R supernodes on the left and K supernode on the right. And as you can imagine, this K is also the parameter of this problem. So if you want to think about it as a parameterized problem, K is the parameter. Now, what do you want to find in this problem? You want to find a labeling where we define a labeling to be a set of nodes on the right where you select exactly one node from each supernode. Okay? So for each right supernode, you can select exactly one node. This is what we call labeling. And just a quick remark, this is different from Bing Kai's notion yesterday because Bing Kai was doing the labeling on the left. So the graph is flipped. Okay, so for the purpose of this talk, the labeling is on the right, okay, and the constraint is on the left. Okay, and what do we want from our labeling? We want our labeling to cover the supernodes on the left, where we say that a labeling cover a supernode UI if there is a smaller node, like a normal node, that is a neighbor to every node in the labeling. Okay, so in this case, for example, this labeling covers the node U1. Okay, and in fact, if you look at it, you see that this labeling covers all the supernode on the left here. Okay, and what we want is to cover as much fraction of the supernode as possible. So we define the value of the labeling, which we write by max cover here, as a fraction of the supernodes on the left that it covers. Okay, and the value of the instant is the maximum across all labelings of the fraction that you can cover. And the gap version of this problem is to determine whether you can select a labeling that can cover all the supernode versus if all the labeling can cover at most S fraction of the supernodes. Okay? Now, just to be clear, we are on the same page. This problem can, of course, be solved in n to the k or n to the k plus 1 time, right? Because you can always enumerate all possible labeling on the right and check whether it covers everything on the left. Okay? Now, from different assumptions, we will show the hardness of this problem when we parameterize it by k. Okay. Now, before we show the hardness of max cover, let's first see how to use max cover to prove the hardness of the problems that we want in the first place. And to do this, the easiest one to start with will be to do the maximum inner product. And just before we go there, I just want to quickly mention that for each of these different reductions, we will use different parameter regimes of label cover. And that's why we can prove the hardness for different problems, both in the P world and the parameterized problems. Okay, so let's start with maximum inner product. For maximum inner product, we will actually reduce from max cover, where k, the number of supernodes on the right, is just 2. Okay, so here there are only 2 supernodes on the right. Okay, and in this case, basically, if your graph on the left is small, right, then you can solve it in roughly n square time, because you just have to enumerate the two nodes in your labeling on the right. Okay, and this is why we can use it to prove like quadratic time problem. Okay, so now, given this max cover, how do we go from here to max inner product? Okay, it's actually fairly simple, right? Let's take every vertex W on the right and create a vector where it's an indicator vector of the neighbors on the left, right? Let's say I take a look at this vertex, this second vertex on the right. It has 3 neighbors, so you just list 1 and 0 as an indicator vector of which of the vertices on the left are their neighbors. And then what's your final instant for the maximum inner product? Again, it's very simple. So you create all these vectors, and you just put the vectors corresponding to W1 into one set, the A, and the vector corresponding to W2 to the other set, B. Right? Why do we do this? We do this because if we look at the inner product, these are 0, 1 vectors. So the inner product are exactly the number of common neighbors they have in the left, which is exactly the number of supernodes that are covered by these two. And these two, since they are from different set W1, W2, this is just the definition of labeling. Okay? So that's it. That's a gap preserving reduction from max cover to max inner product. Yes. You're just one. This is your question, right? Yeah. So I lied to you a little bit, and Saket already caught on. I lied to you because the inner product is the number of common neighbors. But in general, if you look at general instance, you could have more than one common neighbor in the same supernode, right? So it might not be exactly equal to the number of supernode that you cover, you might double count. But it turns out that in the construction that we will look at, this is a probability you get for free. So for every pair of neighbor, you have at most one common neighbor in each left supernode. Okay? And this is why I say that we need some specific properties of label cover when we do this reduction. Either properties like this or, as you will see in a moment, some specific parameter regimes to make the reduction work. Okay, so is the reduction from max cover to inner product clear? Okay, if it's clear, then I'll go to the second one, which is the closest pair problem. Okay, it turns out that for closest pair, basically you don't have to do anything. Like trying to maximize the inner product and trying to minimize the distance is roughly the same thing. Except that you have to make sure that each vertex has the same norm. But this you can do pretty easily using some padding. So you can create extra coordinate and pad to make sure that every vector that you create has the same norm. And the same norm can be the number of vertices on the left, for example. Okay, once you have that, the vector are of the same norm, then the distance square, the square distance is just 2 times the norm minus the inner product. And so what this means is that since we said before that the maximum inner product is exactly the number of vertices you can cover on the left. And what is the number of vertices you can cover on the left, the super vertices you can cover on the left, is exactly R times the max cover, right? The value of the instance, right? Where R here is the total number of supernode on the left. Like recall that we define the value to be the fraction of nodes that are covered. Okay, so, but what is the gap that we get here? Okay, this expression look a little bit strange, right? Because it's not exactly a scale of the value. Like before we get exactly some R times the value. That's why it's exactly approximation preserving. But here it doesn't look quite like that. So let's just write this out to be clear. So let's say we start with an original max cover that has a gap of 1 in the yes case versus epsilon in the no case. Okay? So now what happened in the closest pair problem? In the yes case, the optimum will be 2 times u minus r, where u is the total number of vertices on the left. In the no case, instead of minus r, it will be minus r times epsilon. Okay, so if you look at this, the ratio will be roughly 1 minus some dependency on epsilon times r over u. Okay? And what is r over u? R is the number of supernodes on the left, right? And u is the total number of nodes. So this you can bound to be at most 1 over the size of each supernode, right? The size of each supernode ui on the left. Okay? So if you want a constant factor, you want this parameter to be a constant. So indeed, we will give a hardness for max cover such that this left alphabet size or the size of left supernode is a constant. Okay? As I said earlier, for each reduction, there is different requirement for the parameter regime for it to work. And this is one such requirement. Okay, so that's a closest pair. So inner product and closest pair are fairly similar. The last one is dominating set. So for this one, I will not write out the reduction fully, but it's a classic reduction by phi k where you use this like hypercube gadget. And the summary of this reduction is as follows. So you can get you can reduce the dominating set in such a way that in the yes case, if your max cover is 1, you can cover everything. Dominating set has size k. In the no case, if you cannot cover more than epsilon fraction, then the dominating set has size at least k times this strange looking factor, which is 1 over epsilon to 1 over k. Okay? And there is also a size blow up, so it's not exactly polynomial time in all regime. And in particular, this blow up the main blowout factor is this factor, which is k to the size of the left alphabet. Okay, the size of the left alphabet is in the exponent here. Okay, so from looking at this, you can see that the approximation factor is only 1 over epsilon to the 1 over k. So if you set epsilon to be constant, that's not enough to get a constant factor, because you would get just 1 plus 1 over k hardness factor. So you actually need epsilon to be little o of 1. So you need the gap at the beginning to be super constant. Second thing is, as this like left alphabet size parameter is in the exponent, you want a running time that is polynomial. So you want to make sure that this is little o of log n. Okay, so this is a kind of different requirement compared to the previous two requirements. And also note here that this reduction is for general k, right? Whereas in the previous two problems, we use k just equals to 2 only. Okay, so those are the reductions from max cover to this problem. So let's get back to what is perhaps the most interesting step, right? How to reduce from the problem to get the hardness of max cover. Okay, and for this we will do it through some communication protocol. And to do that, I need to introduce the model, and this is called the simultaneous message model, or simultaneous message passing model, or SMP. So the model is as follows. There are k players, each of the, and also the referee. Each of the player has input xi, which is a length m bit string. And what you want to do is, everyone together, they want to compute some function on this x1 to xk. Okay, some Boolean function f on this f1, x1 to xk. But the communication here is very limited. So the only thing they can do, they cannot talk to each other, they cannot do anything. There is only one turn here. They just get the input and they send some message directly to the referee. Okay? And we also allow the protocol to be randomized. So what does randomized mean here? It means that before the protocol, there is some shared public randomness. So we draw some random string, and we show this random string to everyone, to the referee and all the players. And they can all use this random string in this protocol. And what do we want from our protocol is as follows. First, we want that if this function value is 1, then the referee should say accept always. Okay? The referee should accept with probability 1. That's the completeness. For the soundness, if this function evaluates to 0, then you want to make sure that the referee rejects with a certain probability, or accept with probability at most s. And this s we will call the soundness of the protocol. Okay? So this is a randomized protocol. In one of the protocols that we will use, we will in fact use an even more advanced version of this. But before I go there, let me just mention one thing very quickly here. There is a big difference between communication protocol that we use here versus a standard like PCP machinery. Because here in the communication protocol, we assume that everyone follow the protocol. So there is no one that is trying to cheat here. This guarantee both the completeness and soundness assume that everyone follow the protocol. Whereas if you think about PCP, the goal of having the proof is to make sure that the prover cannot fool you. So the prover is actually actively trying to fool you. This does not happen in this communication protocol setting. Okay, and as I said earlier, for one of the protocol, for one of the reduction, you in fact need a slightly more powerful protocol, which is the Merlin-Arthur protocol. So the setting is almost the same, except with just one thing, which is that there is an all-powerful Merlin who just give you some advice mu. Okay, like give the referee some advice mu at the very start of the protocol. And now the referee can use this advice mu to decide whether to accept or reject. In the completeness, you want to make sure that there is at least one advice that makes the protocol accept. And in the soundness, you want to make sure that for all advice, the acceptance probability is at most S. Okay? And the advice here, you should think of it as having lengths much smaller than the input. So little o of m. So our input length is m. This should be little o of m. And note here that this is the closest thing to someone trying to cheat in this protocol, because in the no case, you actually want a soundness that hold against all mu. Okay? This is the only thing that is kind of possibly cheating in the protocol. Whereas in the randomized setting, everyone is honest and straightforward. Okay? So other setting of randomized and MA protocols clear in this setting?
So you let it choose, like that it selects it, or it's like?
Yeah, it's like someone all powerful give it to you. Yeah. Yeah. Any additional questions?
Why are we assuming the SMP model here instead of something more like DRAM? Am I missing?
We will see it in the reduction. Like it's an interesting question, but it turns out that SMP give you exactly this max cover, like once you write it out in terms of reduction. Yeah, but we're gonna see it in a moment. Yeah.
Thank you.
Okay, if there is no additional question, then let's proceed to and see one of the reduction. So when I wrote this diagram, there is a middle part that say PSP, this product space problem. And indeed, for some of these problems, we have to do a pre-processing so that it's in this like nice form. But it turns out that one of these hypotheses is already in the nice form, the K-sum hypothesis, which is why I emphasize K-sum at the beginning. So let's do the reduction from K-sum directly before even talking about the PSP. Okay, and we'll come back to talk about PSP and the other assumption later. Okay, so recall that again in K-sum you have K sets. You want to pick one number from each set such that the sum is 0. Okay, so what is the corresponding communication problem? I mean, in K-sum it's kind of clear. The corresponding communication problem should be this, what we call sum 0 here, which is each player I receive the input xi, which is an integer, and you want to check, together they want to check whether the sum of xi is equal to 0. Okay, this is the sum 0 problem. And again, we assume that each xi is not too large. It's no more than n to the 2k in magnitude. Okay, so there is one kind of very nice and also kind of one of the first protocol you would try to use in this setting, which is to try to do random modulo, right? So consider the first, say, log m primes. Here I use r to denote this log m. Then you use the shared randomness, right? Remember there is a shared randomness that the referee and the player can use. Use the shared randomness to randomly pick one of these primes. Okay? I denote this by P star here. So once you pick P star, what do? Each player just send their number mod P star. And the referee just check that the sum is equivalent to 0 mod P star. Okay, that's it. Very simple protocol. So let's see why this protocol works. I think the completeness is pretty clear. If the sum is 0, then obviously it's 0 for any mod. In the soundness, if the sum is non-zero, since you know that the number are pretty small, then they cannot have too many prime divisors. So if you pick the r to be large enough, like roughly log of n to the k, then you get that the probability that you hit a non-divisor is pretty large, and the soundness, you can bound it, let's say, to be at most a half. Right? So this is a pretty simple protocol. Yes?
Why are they not just setting xi itself? What are you trying to minimize?
Yes. So it will, it will show up in a moment. So the point is this, right? The input, we start off with m bits, but here the primes are pretty small. This prime, the largest prime we need is only log m. So the prime that we need is only m, at most m. So the message that we have to send has length is only log m bits instead of m bits. So that's the saving that we get. Okay? But at the same time, we have to randomly sample this prime. So we also need the randomness of about log m bits. Okay? So now, how does this protocol relate back to label cover? So here's how you can construct a label cover given this protocol and the k-sum instance. Okay? First, I will construct the right-hand side of my label cover using the input to the k-sum instance. So recall that the k-sum instance, you have k sets. So I just create one super node for each set, A1 to AK, and each node just corresponds to an integer in that set. Okay? So this is my right-hand side of the label cover. How about the left-hand side? First of all, I create one left-hand super node for each possible prime that I might use as the modulo. Okay? How about the nodes? So I'll create one node for each possible combination of k number whose sum is 0 mod that prime. Okay? So these are the k messages that could be sent, and my referee would accept those messages. Okay, now how do I link up the graph? I link up the graph based on modulo. So for each number on the right, I look at the modulo, the value mod p1. So if I'm in the I set, I look at the value mod p1, and I look at the I coordinate of the value on the left. If they are equivalent in the mod p1, then I just add an edge. Okay, so or in other words, maybe something that is easier to say here is that each node in the left-hand side is a combination of k messages that could have been sent that the referee would have accepted. Okay? Now the edge says that this I player can send the I coordinate, can send the I message corresponding to that vertex on the left. Okay, so it's kind of a check that they can send that message. Yes. A1 to AK are the input to k-sum problem. So in k-sum, you have k set A1 to AK. And in each AI, you have a bunch of numbers. So each of the number becomes one vertex. Yeah. Yeah, so the size of the graph on the right-hand side is n, right? The same as the size of the k-sum. It's k-sum problem. Pardon? Yeah, so the size of the graph on the left side. Okay, so the size of the graph on the left side will depend on the parameter of the protocol, and I'll talk about that in a moment. But as you can see, if you don't do the modulo, right? If you just have this one giant node on the left, then you will have to take all the combinations of integer whose sum is 0, and that would blow up by too much. By reducing this, you actually reduce the left-hand side. That's why this reduction, this modulo is required in this setting. But we will come back to this in a moment. Yeah. Okay, now a labeling, what does a labeling mean? A labeling means that you have to pick one node from each set AI on the right? So this is exactly also correspond to a solution that you would pick in k-sum as well. And if the sum is 0, then since the sum is 0 mod p as well, then you can see that there has to be a node on the left that is a neighbor of everyone on the right. Okay? And the soundness also follow from the protocol as well. because for each prime, if you cover some vertex on the left for that prime, then it means that you are 0 mod that prime. Okay, so the fraction of nodes on the left that you cover is exactly equals to the acceptance probability of the protocol. Okay? So that's it. That's the reduction from K-sum from max cover. But now I will take before we go forward, is there any additional questions about this reduction? Okay, if there is no question, let's take a step back a little bit and I'll formulate this PSP like product space problem more formally and see how product space problem plus any communication protocol give the max cover and also answer your question about the relationship between different parameters. Okay, so what is product space problem? So in short, product space problem is a problem where the input is a bunch of set A1 to AK, and you have some predicate F, and the predicate shouldn't depend on the input, okay? It can depend on the input size, but not the input itself. And what do you want to check? You want to check whether you can select one element from each set that satisfy the predicate, okay? So there is a bit more, like if you want to be formal, you have to parameterize based on the problem size and so on, but this is not too important here. And yeah, for the rest of this talk, I will think of the input element as being of length at most log n. Okay. So that product space problem, as you can see, the K-sum hypothesis is exactly just the product space problem, where the predicate that you check is the sum 0 predicate that we just talked about, right? Because we have K set and we just want to select one element from each set that satisfies this predicate, this sum 0 predicate. Okay? Now it turns out that for the other set, you can also for the other hypothesis, you can also state it in this way as well. And I'll state it for you in a moment. But for SETH, the predicate that you can use is set disjointness. So you can think of each xi as a set, as a subset of M encoded by 0, 1. And you want to know whether all these sets are disjoint. Okay, the predicate check whether all the sets are disjoint. And finally, when I say all the sets are disjoint, I mean the intersection of everything is empty, not pairwise intersection, the intersection of everything. For multi-equality, I don't have it here, but because it's a bit hard to write down. But to say in words, in multi-equality, each input is a partial assignment, and the multi-equality checks that the partial assignment do not contradict each other. Okay, so you have a bunch of underlying variables, and each input assign value to some variable and leave some blank, and you check that there is no inconsistency. Okay, so let me quickly show you how to state like a standard hypothesis in terms of this like product space problem. So for SETH, it's actually the same as the reduction to orthogonal vector, if you have seen it. So the way you do it is you partition the set of variables into K sets. And for each partial assignment to each, so you create one set per each partition. And for each set, you look at all the partial assignment to this xi, to the set of variable xi. And your vector denotes which clause you have already satisfied. Okay, so if you have satisfied the clause, then that's 0. Otherwise, it's 1. And basically, what you want to check is whether you can select k element such that the intersection is empty, which means that you satisfy all the clause. Okay, so the exact syntax is a little bit cumbersome, but it is not very hard. For ETH, it's kind of similar to what we see yesterday, which is instead of partition the variable, you partition the clauses. So once you partition the clause, you can have a partial assignment on those clauses. What you have to check is that they are consistent. Okay, and this is exactly multi-equality. Finally, for click, you can also think of click as instead of selecting the vertices, you select the edges, okay? Now, once you select the edges, so you can say, okay, the first player select the edge from V1 to V2. The second player select the edge from V1 to V3. You only have to check that the V1 of all the players are referring to the same node. That's also equality check. Okay, that's why we can also reduce W1 not equals to FPT, write W1 not equals to FPT in this PSP form. Okay, so once we have the PSP form, now how do we reduce to max cover? This is exactly the same as in the K-sum hypothesis, but we can do it for any SMP protocol. And here is where I will state the parameter dependency. So let's assume that your advice is gamma bit, your randomness is R bit, message length is L. Then here is how you can construct the instance. So first of all, it will not be a carb reduction, so it will be a Turing reduction. You create multiple instances, one instance per possible advice. Okay? So for each of the 2 to the gamma advice, you create one instance. So let's now fix one advice mu. How do we create that instance? This is mimicking what we already saw for K-sum. First, the node on the right are this set A1 to AK. And recall again that this set A1 to AK are the sets that are input to your PSP problem, the things that you want to search over in the PSP problem. Okay? Now on the left, you create one supernode for each possible random string. And now, how many random strings are there? There are 2 to the R, because we assume that here we use at most R share randomness. And for each node, for each supernode on the left, the small nodes, what are they? They are all possible combination of messages such that the referee accepts for that particular randomness. Okay, so these are all possible combination of the K messages sent from the K player that the referee would accept. And finally, you set an edge if the message for player I correspond to that input, the message that the player would have sent at that input on the right. Okay? And that's more or less it. So I will not do the full argument here, but you can see that if you take a look at any labeling, it corresponds to a fixed input to the K players, and it will cover a node UI on the left if and only if the player, the referee would accept for the randomness string I. Okay, so the value of this max cover is exactly the acceptance probability of the protocol, of the SMP protocol. Okay, now what is the parameter? As you can see, there are 2 blowups that I already wrote down. One is 2 to the gamma, the number of instance you have to create, because you have to create 1 for every advice.
So where was this advice possible? So I'm getting it. So where was the advice your protocol?
There was no advice, sorry. I didn't say it out loud, but the previous protocol was randomized. There was no advice. Yeah. The only protocol that needs advice is the disjointness protocol, but the other ones don't need it. Yeah. So there was no advice so far. So 2 to the gamma is the cost you pay for the advice. 2 to the R is the cost you pay for the randomness. Okay? Now there is one thing missing, right, which is the message length. So what do you pay in the message length? So what you pay in the message length is this. Remember that for each supernode, you create this small node based on all the combination of message that you accept, right? But how many combination of message are there? These are K times L bit, because these are messages from K player, each is L bit. So the left alphabet size can be as large as 2 to the K times L. So for our purpose of the reduction, since we want to make sure that the blow up is sublinear, is subpolynomial. We want to make sure that the gamma and the r is little o of m. Recall again that m is like log n here. But we have a more stringent requirement on the L, because remember that for dominating set, when we do reduction, we actually have an exponential blow up in the left alphabet size. So we want the left alphabet size to be at most log n already. Okay, log n, which is m, and here is also exponential in L. So we want exponential in L to be at most m. So the left alphabet size can be at most log m. Not the left alphabet size, sorry. The message length L can be at most log m. Okay, so this is like the requirement of the parameter. And in fact, if you want like closest pair, you need the left alphabet size to be smaller, because as we discussed earlier, we need it to be constant. So this left alphabet size L, the message length L has to be constant. It can't even be super constant. Okay, so that's the parameter. I want to quickly tell you a little bit about the protocol. I won't go into any detail. So it turns out that the protocol I show you for K-sum, the modulo protocol, actually it doesn't work yet. The reason is that the message length is still log m. Whereas, as we said in the previous slide, we need little o of log m. But fortunately, there is the protocol of Viola, which by itself also doesn't completely work, because while it has a very small message length of O1, the randomness is very large. But you can compose this protocol and get kind of the best of both worlds. And this is what satisfy our constraint and give the hardness that I told you earlier. So that's K-sum. For multi-equality, again, I will not go into too much detail, but the protocol is very, very simple. This is the entire protocol here. Basically, each player just encode whatever they receive in the partial assignment, and then together everyone pick a random position of the code, and then the referee just check that all the message it gets are consistent, and that's it. There is no like super complicated machinery at all. Just standard error correcting code, and this give you what we want. And again, this gives the hardness from ETH and from W1 not equals to FPT. This is very simple protocol. Now here comes the last one, which is a little bit more complicated, which is the protocol for set disjointness. And this is the one that you need the advice. So it's known, is well known that if you don't have any advice, then you cannot do anything that is sublinear for set disjointness. And so I think I will not go into the detail of the protocol, but basically it uses some code that is that has some nicer property. Like you can think of it as some sort of polynomial where the codes, when they multiply together, it is a code word of another code. And you can use this to give a protocol. And it turns out that you can use the like a standard polynomial code like read Solomon directly, because the parameter is not good enough. But if you use some algebraic geometric code, then the parameter is good enough for this kind of reduction to go through. And this is required for the hardness for closest pair and for the SETH hardness for dominating set. Okay, so I will wrap up here. So today we saw a distributed PCP framework that through like communication protocol can give you reduction that show hardness for these different problems like closest pair, inner product, and dominating set. And there are still quite a few open problems that are left. Like there are some obvious ones, like you can ask, okay, is dominating set totally inapproximable under W2 hardness, right? So as I said earlier, constant factor is now known, but beyond constant factor is still not known. I think this is a more like open-ended one, but are there like natural like product space problem for which the predicate doesn't have a good protocol. Like basically, are there any product space problem you can think of that kind of the reduction doesn't go through in this framework? Okay, and I should mention here that there are already sort of some natural problem like for example OV with a large domain, large dimension. This could fit here, but I guess the question is like, are there more, or is that just it? And finally, I think it's kind of also interesting to think more about like what we can do using this framework or this style of framework, like as was alluded to earlier, right? Like this, it's not clear why simultaneous message passing is the right framework. It's just that it gives us the reduction from max cover. Maybe there are other type of communication protocol that give a reduction to some other problem that we can use to prove some other hardness. And even within this distributed PCP and simultaneous message passing, maybe you can design a more elaborate protocol that give better hardness for some problems, right? Like currently the reduction is completely generic. It doesn't use any property of the protocol. But you can imagine, you can use the fact that the referee has certain predicate that it verify or something like that to prove specific hardness, better hardness for certain problems. I think that's an interesting possibility that hasn't been fully explored yet, as far as I'm aware of. Okay, I think that's all that I want to say. Thank you everyone again.
Any questions?
So in the protocol you use error correcting, because which part of the protocol you use randomness?
Which part of the protocol that we use?
You use randomness.
Oh, yeah. So in both protocol, but maybe it's easier to see for multi-equality. Maybe it's easier to see for equality. So let's say everyone has were given a number, and they want to check whether they are equal. The way we can do this is to encode it in error correcting code. But instead of sending the entire code, you send a single position. But you have to align the position, right? If you send different position, then they cannot be checked. And that's the randomness that you use. You use the randomness to jointly sample the position you want to send on your error correcting code. Yes.
So for the dominating set problem, if I understand correctly, the up boundary is a to the k plus 1. Dominating set problem. The lower boundary is a to the power of k minus 2.
Yeah.
So there is a 1.
No. For dominating set, there is actually an upper bound of n to the k plus little o of 1.
Oh,
Yeah. There is work from Pasin Williams that shape of this one.
Okay.
Yeah.
That's time.
Why is it called distributed PCP? Is this somehow like mirroring how the PCP theorem is written?
So Amir was the one who named this, so I will give it to him.
I guess it's because there's like two players and they're doing the PCP together. Like
The original formulation is with a SAT formula, and each one of them corresponds to half the variables. So you distribute your witness, because what is a witness is an assignment to n variables. Half of them has an assignment, one assignment, the other one has the other one. It's distributed, and together can they still conclude it's a valid assignment or not. You can clap again.